I'd like to introduce Lane Wigley, presenting Revisiting Power Provisioning for High Bandwidth Routers. Lane is a technical marketing engineer at Cisco and joining us on stage from North Carolina. This is Lane's first time presenting at NANOG, so welcome.
Hey, thank you. Down to the end, I hope it's not because your flights got canceled, but really appreciate everybody here this week. If we can go to the first slide here. So I've been working with this kind of routers since about 98 or so, and this isn't a pitch from my product, but it's just about a project that I've been working on recently, and I want to kind of start the discussion so that if some future nanogs, maybe we can kind of talk about how we can find a better way to provision power, both from the, what the routers are asking for, as well as how we navigate that in facilities and planning for cooling and things like that. So what are the characteristics of what I'm calling big routers? They have modular fabrics, they have multiple numbers of line cards, lots of optics options. I'll talk about how that's becoming more relevant in the range of optics that we have these days. Modular power supplies. My system has up to 24 power supplies you can put in it. And the other thing, which I know causes a lot of challenges, is that we often want the sheet metal for these devices to be in place for a while, 2, 3, sometimes even 4 or more generations, in which their power is going to go up. And so from my view on the, the vendor side, is my understanding of your challenges is that goal number 1 is to prevent brownouts. We don't want the system running out of power, obviously, but often we put in a lot of margin to keep that from happening, and sometimes it might be too much. When brownouts happen, they're not clean failures. Some transistor runs out of power, but it could be a different one each time, so it's not clear exactly what happened. The other thing from provisioning is to accurately represent cooling requirements. One of the common questions I would get from people I work with, they'll say, Lane, you told me I needed 10 power supplies, but it looks like I'm only using 3. Why is that? And in some of the graphics in the next couple slides, I'm going to kind of explain why some of that is just how it is, as well as some of the things we can actually do better now that we have more and more variation as well. Other things we want to do is minimize costs. When I talk to a lot of people inside our company, they often think, okay, power costs 12 cents per kilowatt hour or something like that. They don't understand that in our world, we have cooling and PUEs and batteries and all this stuff. And so it ends up being a lot of costs. I tend to use, in my mind, $5,000 per kilowatt per year, just based on what some people have told me they pay for protected power from their vendors. But it ends up being a pretty big number. Another thing that's really important is obviously fitting in the budget. For some of our partners, it's about having as many servers as they can on the area. For others, it's around putting in more networking equipment. And then the last big one, which I think is an operational challenge that I'd love for us all to have some discussion about, is this challenge about how not to get stranded. If I need 10 kilowatts now, but I might need 40 kilowatts 10 years from now, do I go ahead and start paying for those 40 kilowatts? Because what I really don't want to have happen is to need those 40 kilowatts and it's all gone. Or is there some way to have maybe options on the power or some system to make these reservations ahead of time? Okay. So there is some level of typical versus max power, which is just unavoidable. And so here's a system, and I've kind of blocked out my logos just for a little fun here. And this is one of the ones that I work with. And if you start on the left side with the green, those are the line cards. And the line cards have some amount of power when they're just turned on. Then as you add terabits per second or billion packets per second, they need more power. And those dark green are the difference between a typical power and a max power. Max power happens when you put small packets at 100%, you're putting more load on the chip. Next to that, we have the optics. And one thing you're seeing increasingly being the case with 400 gig is that optics have a much wider range of power. What that graphic is showing is on the top you have some cards with gray optics for 400 gig, then you have some with coherent ZR plus optics, and at the bottom you have them with 100 gig optics. And so with 100 gig optics, we're really going from 3.5 up to 4 watts. Now we're going from 12 watts up to 20 plus watts. So there's a huge range of what you could put in, and even in some systems you have copper cables. On the right side, I'm kind of showing the range of power for the fabric, and each of these full blocks is 100 watts, just to provide some scale there. The difference between typical and max on the fabrics are usually not as much. But the fans are where things get really interesting. Fan power is a cubic function of how much air you're moving. So if you're running a fan at 20%, that's dramatic. That's not a fifth as much power as if running at 100%. So what I'm showing here is those little squares on the left side. That's going to be your typical fan power. But if you need to step on the gas and go to 100%, you could be using 10 times as much fan power. That's kind of unavoidable. We want to have that in reserve in case the temperature goes up, maybe the chips get hotter, etc. But it's sort of unavoidable. There are some things we can do, though. And one of the areas that I've been focusing on is how we handle optics, and this is for the platform I work on. Again, I mentioned that if you go back far enough, the optics were just on board. They were part of the card, and we've always just budgeted them as part of the card. Even relatively recently, we would just assume that you had LR4 optics on all the ports, and we would connect that into the system or into the line card. But now if you look at some of the cards, I've got, I think one of those is mine, one of those is some other vendors, we have maybe 48 ports on a line card or 36 by 400 gig. If you multiply by 36 ports by 22 watts for ZR plus optic, for another 2 watts you need to do some voltage conversion there, you're very quickly in the 800 watts of power just for these optics, but you might have AOC cables and copper cables and not need all of that. So the way I like to illustrate this is how we can prove our power allocation is kind of 2 ways. On one hand, there's muscle, and on one hand, there's fat. The muscle is stuff that we might need, like the extra power for the line card if we go to 100%, or the extra power in the fabric 100%, or the extra power in the fans if we get a high temperature event. We really want to keep that available. At the same time, there's fat. We don't need power for ZR plus optics if you're running a DAC cable. And so what we've done on the platform I work with is we've actually moved to a model in which we don't start allocating power for the modules until you put them in. Okay? And I don't know if that's what everybody else does and we're just catching up, or I don't know if that's some innovation that I'm encouraging other people to do, but it's a model that gets us a little bit closer to reducing the oversubscription that we that we have been doing traditionally. There's other things you can do. So for example, if you only put 4 line cards and the system takes 12 line cards, you're actually going to, if you optimize, have some things shut down on your fabric cards, you can actually take care of that transaction dynamically. Don't give the line card, the fabric cards full power until the line cards are put in. So you can do some things like that as well. Okay, so the goal is to remove as much fat as we can while having the system still operate. Another benefit of doing this, in addition to saving how many power, your power bill at Equinix, is you want to keep your power supplies efficient. And this is just an example. This is probably pretty low, but a lot of times we don't always think of the efficiency of the power supplies. The power supplies on a lot of products today are probably about 96% efficient from 40% up to 90%. But if you find yourself running your power supplies at 15% of their load, they may be just blowing away 15% of their power just because the voltage conversion is not efficient when they're used so low. So having the right number of power supplies helps both in paying for less power as well as helps the environment and helps generating less heat from that efficiency. So other things that we're thinking about as far as as we go forward, the discussion we could have is how do we treat empty ports? Are they just a missing optic, or are they also some of the chips shut down? We could even cut that back even more. How much margin are the facilities adding? Or are they oversubscribing? I actually talked to somebody this week and said it's kind of like an airplane. We sometimes sell a bit more capacity than we have, so we have to navigate how our system works as well and how the facilities work. What is the optimal max temperature? There's things that we could give you if the max temperature was 35. There's things we could give you if it was 45. What's the right number? when you think about this, there's really, if you want to minimize total power, you want to think about how much power does the system fans take, how much power does the facility fans cooling take, how hot are the chips, how hot are the CPUs, because if the devices actually get hot, they'll start consuming some more power as well. So it's a balancing act between all of those. But getting back to how I was saying we tend to stack a lot of margin to prevent these brownouts, what we tend to do today is we have power so that we could lose a power feed and have the cooling go down and get small packets and go to 100% all at the same time. That might be the right approach. That in some cases, that might not be the right approach in some other places. So we're trying to provide some tools so that you can make those decisions. And then the last thing I think that's really important to figure out is how can we figure out some best practices to solve this problem of, well, I might need this power in the future, but it'd be really expensive for me to start paying for it all now. And then there's a link to some blogs I've written on this topic and some other things on my site. Okay, thanks.
Any questions for Lane?
Steve Ulrich, Risk Networks. Great presentation, Lane. I wonder if there's also a tangential conversation here around how willing are folks to embrace kind of different physical form factor and hardware designs that might facilitate lower power consumption overall. Like a lot of times we have conversations with customers where they're like, want to pack as much stuff as possible in one RU.
Right.
But like if we made the box 3 RU, it'd be a lot easier to cool, and like you're trading off one set of things for another, but we can spin those fans slower, we can cool the box more efficiently. Like there's more room for flex here. So I think, speaking as a vendor, we'd certainly solicit they're curious as to, what are the trade-offs operators might be looking for in the future that way too.
Yeah, so maybe by a show of hands, I'm going to ask who in general is more RU constrained versus power constrained. So who is more RU constrained in general? Okay, so I'd see 1.5. Okay, and who's more power constrained? Okay, so a lot more there. So what that tells me is that maybe it's okay to make a 2 RU tour if the power goes down, or maybe a 2 RU something. And I was having a conversation with Jared earlier the week, because by having bigger fans, you can save money on the power in the fans. Also, by having bigger heat sinks, you can transfer more air through. So there's lots of things to balance out, but that's a great question, and that's excellent feedback. Other questions? Okay, thanks a lot.